Welcome to class meeting 26 of the Introduction to Optimization. So let's quickly review what we were doing last time. So the main topic is the duality. And there were some definitions related to that. So first, we are given a so-called a primary problem. So the primary problem considered here is in this form. We want to minimize an objective function f0. Of course, here x is a length n vector subject to we have equality constraints in the vector form. Inequality constraints in the vector form. I use f0 and here f underscore, and have equality constraints also in a vector form. So this is an optimization problem, a constraint optimization problem with inequality and equality. Now, given that, here goes our definition of the Lagrangian. L of x lambda nu, defined as the summation of the objective function and linear combination of inequality constraint functions. So it can be written as lambda transpose f underscore of x, and also another linear transpose, linear combination of nu transpose times h of x. Here, lambda and nu are called Lagrange multipliers. First, lambda is the Lagrange multiplier associated with inequality constraint function, and nu is the Lagrange multiplier associated with the equality constraint function. Here, we intentionally choose that lambda vector that has the same length as this inequality constraint function is restricted to the first ordinate. The reason is, of course, you can define L without having this constraint, but it's useless. And also, if I do not repeatedly say lambda is greater than or equal to the zero vector, you may get confused someday. So I will emphasize this. So we define the Lagrangian like this for lambda greater than or equal to zero vector. Then, what kind of property we have? So let's compare with the objective function value at some feasible x first. So for x feasible, which means that for x in omega, f0 of x equals what? Actually, not equals, greater than or equal to L x lambda nu for lambda greater than or equal to 0. Why? Why this holds for x feasible? Because this is 0 first, due to this constraint. Okay, x feasible means h is 0 vector, but f is less than or equal to 0, but lambda is greater than or equal to 0, term by the entry by entry. So if we inner product them, we still have non-negative value. So right hand side is less than f0 of x. So we have this lower bound property. Now we have another definition. The Lagrange dual function. I'd better say a Lagrange dual function because it's not unique. We are going to use G, function of lambda and nu, as inf of So given lambda and nu satisfying this condition, we infimize the Lagrangian, where x is in some set omega prime that contains the constraint set. So before, x feasible meant x is a member of omega. But now we consider a bigger set omega prime in R to the n. Such increase of constraint set is called relaxation of constraint. Okay, so this means relaxation of constraint. Got it? One simplest omega prime is what? This is one simplest choice of omega prime that is defined as domain of f0 intersected with domain of f underscore intersected with domain of h. So all the functions involved in our primal problem can be evaluated at x in omega prime. Our textbook chooses this domain of the involved functions to define the Lagrangian dual function, but it's all up to you. Because what we want to do is that we want to derive G, or sometimes we want to utilize G for our convenience. So sometimes this is not useful. This is not a useful choice as omega prime. Sometimes. Got it? So there may be different Lagrangian dual functions. Now, what can you say? By the way, now these are variables that determines the value of G. So before, when we define the Lagrangian, we call these two as the Lagrange multipliers. Now we alternately call them as dual variables. Because now we view these are variables for G. Okay, so actually they are actually the same, Lagrange multipliers and dual variables. Still, you must focus on this condition. Otherwise, it doesn't. It is not useful. Okay. Now, here goes the definition of the dual problem. But it depends on our choice of a Lagrange dual function. So let's say a dual problem. A dual problem is now a maximization problem. Maximize the Lagrangian dual function with respect to lambda and nu. Here our constraint is simply the lambda vector, that the dual variable lambda is greater than or equal to the 0 vector. Now, what is the property? Let's say the optimal value of G is D star. So here, max of G subject to lambda greater than or equal to 0 as D star. And similarly, let's say here the minimum value of f0 of x subject to x in omega as P star. Then what can we say? P star is always greater than or equal to D star. Whatever dual function you choose. That was the result. So this always holds. And this is called the weak duality. By the way, sometimes the P star equals D star. In that case, we say that the strong duality holds. Unfortunately, we do not have the necessary and sufficient condition for the strong duality to hold. We have many examples, and we have many sufficient conditions. What does that mean? If such and such conditions are met, sub-conditions, collectively they are called a condition, a sufficient condition. If these sub-conditions holds, then what? P star equals D star. One of the best known such sufficient condition is Slater's constraint qualification. So remember this. This is one famous sufficient condition for the strong duality to hold. What was that? This qualification only applies for convex problem. What does that mean? Our primal problem is like this. Here, the equality constraint is what? Equality constraint function is affine. Ax minus b. Got it? So in Stephen Boy's convex optimization, the convex optimization problem in a standard form looks like this. So the equality constraint function is always affine. Now, f0 and f underscore are convex functions. On the convex constraint set. By the way, this is the intersection of the domains of f0 and f underscore and this explicit constraint. By the way, you can show that if f underscore is a convex function, then this sub-level set. So let me a little bit enumerate. So you have something like this. So P. Got it? So the first condition, you may say that this is a set. This is another set. Here goes another set. They must be all intersected, right? This inequality constraint can be rewritten like this. The first function value is less than or equal to 0, scalar. Second function value is less. So each sub-constraint set must be intersected because this means that they are all ended. Okay? And if this is a convex function, with equality, this is a level set, and less than or equal to some constant is called a sub-level set. So this is a sub-level set. Interesting thing is that the the sublevel set of a convex function is always a convex set. So each one is a convex set. And another interesting thing is that intersection of convex sets is convex. So this is convex. And we know that this is a convex set. So intersection of two convex sets are also convex. Got it? Anyway, you will study these properties in convex optimization course. By the way, I contacted one of the professors in our industrial engineering department, and he said that there will be another optimization theory course offered by their department next semester. So if you want to have some kind of other view about this kind of optimization, by the way, their title, the title of their course is non-linear programming. Okay. 비선형 계획 in Korean. So if you have interest, please take. Okay. Anyway, it's up to your advisor. Your advisor might say that, hey, they are the same problem, same course, don't take. But anyway, you may enjoy different point of views in different departments. Anyway, so Slater's constraint qualification applies to this form of convex optimization problem. So it's the kind of very restricted, has restricted application. General convex optimization problems are stated like this: minimize a convex function defined on a convex constraint set. And as I emphasized, some convex constraint set may not be written in this form. Got it? So this is a very special case. Anyway, Slater's constraint qualification requires first convexity, second the interior of D. By the way, what is D? D is the domain of this objective function and the inequality constraint function. By the way, what is domain of this one? Any x in Rn, right? So this D is intersection of the domain of F0 and domain of F underscore. Here, int means interior of this. So you remove the boundary. And then you intersect this set with two sets stated by our constraint sets. But here, as we remove the boundary, we also remove the boundary here. So first we have this curvy inequality without equality, and we have the equality constraints. Got it? Second condition, first condition is that the problem is a standard convex function, convex optimization problem. And second, this set is not empty. It's not an empty set. Then what? If these two conditions are satisfied, you can say that the strong duality holds for that primal problem and the dual problem you find. Very strong. Sometimes it's very easy to show. By the way, I have drawn this Venn diagram again and again so that it may be imprinted in your brain whenever you think about optimization problem. So this is the set of all constrained optimization problems. Then here is a big set of convex optimization problems, and here is a big set of constraint optimization problems with inequality and equality constraint functions. What does this mean? The problem looks like minimize f0 of x over x subject to f underscore x is less than or equal to 0 vector and h underscore of 0 vector equals 0 vector. Got it? And what about this one? As I told you, you minimize a convex function over a convex set. So here, this is convex and this is convex. Got it? There is a very important intersection between these two subsets of problems. And you may say that, this subset is the set of convex optimization problems with equality and inequality constraint functions. But here, among them, we have another subset called convex problems in a narrow sense or convex problems in standard form. And as I just told you, this is in this form. You have convex objective function and convex inequality constraint functions, but affine equality constraint functions. Got it? And I repeatedly told you the convex optimization textbook and the course is mainly about the problems inside this subset. And fortunately, we have linear programming problems here. Got it? Now, when can we apply the Slater constraint qualification? Here. Got it? Of course, not every convex problems satisfy strong duality. I say that you may apply. I'm not saying that you have strong duality. Got it? Some of the problems may not have the strong duality. And this is the review, very long. And here goes what to do today. First, we study so-called complementary slackness. And when I was taught this Introduction to Optimization course, complementary slackness was taught only for linear programming problems. But I give you a general form today. So please open your Stephen Boy's lecture note I've given you. And you have complementary slackness in page 5-17. If you just self-study this, it may take a lot of time before you remove confusion. So I help you right now. Complementary slackness is stated this way. Okay. It's a kind of lemma. Whenever you have lemma theorem, usually it's in the form of a statement. If blah blah blah, then blah blah blah, right? So complementary slackness is also have such a statement, and the statement is like this: if x star is primal optimal. What does that mean, by the way? This x star is the optimal solution, unoptimal solution. I need to be careful. X star is an optimal solution, one of the optimal solutions of the primal optimization problem. Second, lambda star, nu star is dual optimal. What does that mean? This lambda star, definitely here, lambda star is greater than or equal to 0, according to our definition of the Lagrangian dual function. And these are optimal this pair is an optimal solution of the dual problem. Got it? So we assume that there is a primal problem given and we derive the dual problem. And P star equals D star. Then what does that mean? The strong duality holds. Got it? So X star is primal optimal, lambda star nu star is dual optimal, and the strong duality holds. Got it? So given this condition, we want to have some consequence. And that consequence is interesting and stated like this. Lambda I star is greater than 0 implies Fi x star equals 0 for all I. Okay? So you test by changing I and check this whether this holds. If this is true, then this is true. By the way, if you don't like that, just remove. But what's the contrapositive of this statement? What is the contrapositive? If this is not true, then this is not true, right? So actually this then part is same as what? Fi x star is less than or equal to 0 means lambda I star equals 0. Why? Why I say a little bit differently? Because x star is primal optimal means x star must be a feasible solution. If x star is feasible, what happens? Fi is either 0 or negative. So the negation of this statement is this one, right? Got it? It's not like Fi is greater than 0 or less than 0. It's impossible because x star is feasible. Got it? And second, lambda sub I star is not greater than 0. And you may say that it may be equal to 0 or less than 0. Okay, is it true? Let me see. Just a second. Yeah, let me check. 0 less than. Yeah. Let me see. Is it true? Yeah. But less than 0 is impossible because when we define our Lagrangian and Lagrangian dual function, we assumed lambda i's are always greater than or equal to 0. Got it? So these two are the same. But unfortunately, our handout states little confusingly. For example, take a look at the last line of our 5-17 page. Okay? Now compare with this one. Now, why this is called complementary slackness? By the way, slack means loose, okay, not tight, which means that not equal to something. Now, let's see that. If lambda I is not equal to 0, then corresponding Fi must be 0. Here, Fi is not equal to 0, then lambda I is equal to 0. So this part is that if something is not equal to 0, the associated function or Lagrange multiplier must be 0. This is why this result is called complementary slackness. Complementary, okay. Non-zero, 0. Non-zero, 0. Got it? Now let's prove this lemma. And this is also confusing. Okay. So we start from this one. P star equals what? By definition, that is mean of F0, but actually that is what? F0 of X star. Am I right? because x star is primary optimal, so p star must be f0 of x star. And this is equal to what? D star, what is that? That is g of lambda star nu star. Am I right? Right? Now, so far, so good. Now, we use the definition of this Lagrange dual function. What is that? That is infimum of something, right? So, let me write it down like this. This equals infimum x in, let's say, d of f0 of x plus lambda star transpose f underscore x plus nu star transpose h underscore of x. Am I right? Remember, by dropping these stars, this is just a definition, right? So if you evaluate g at lambda star and nu star, you just replace lambda with lambda star and nu with nu star. Am I right? So this is simple, just restatement of our definition at lambda star and nu star. No problem, right? Now, let's compare this one with let me write it like this. L x star lambda star nu star. By the way, why this inequality holds? Why? Here, given a Lagrangian L of x lambda nu, suppose you just evaluate that one at some x star lambda star nu star. Now let's compare that with this one. This one here, x may not equal to x star. We don't know, right? But this is infimized version of L. So that's why this holds. Got it? In general, here the solution to this optimization problem may not be x star. May not be. But we assumed it's the strong duality holds, so we will see that that is true. But anyway, so this is by, again, by definition of L. Okay? This is simply infimization of L at lambda star nu star. Now, what about this one? If you restate this one, we have f0x star plus lambda star transpose fx star plus nu star transpose h star. But the third term is 0. Why? Because x star is feasible, which means that h of x star equals 0. So we have now equals f0 x star plus lambda star transpose f underscore x star. Am I right? Now, lambda star is what? Dual optimal. What does that mean? This is greater than or equal to the 0 vector. Now, x star is primary optimal. What does that mean? F underscore is less than or equal to 0 vector. If you inner product them, what is this scalar? This scalar is less than or equal to 0. So what can you say? Am I right? For example, this is minus 3. Then definitely this holds, right? But we've already shown that this term is lower bounded by this upper bound. What does that mean? They are all the same. So this must be what? This must be 0. Got it? This must be 0. Now, what does that mean by this is 0? summation lambda I star fi x star equals 0. And what does that mean? As I already told you, lambda i's are greater than or equal to 0, fi's are less than or equal to 0. So this product, each term is less than or equal to 0. If you sum some terms less than or equal to 0, then you have 0. What is the necessary and sufficient condition? Each term is 0. So here, for all I, now what? If lambda I is greater than 0, this must be 0. Am I right? Am I right? So that's why we have this. Got it? So this is the derivation of the complementary slackness. And complementary slackness, you may say that it's a simple consequence of strong duality. Yes, but this condition may be saying that this is 0, or sometimes this holds, or sometimes that holds. But you can remember like this. And this appears as one of the conditions of the Karush-Kuntaka conditions we are going to see. That's why this is so important. And now let's see another one. So this is Karush-Kuntaka. By the way, sometimes some people have named Kun like this, but this guy says K-U-H-N, not K-H-U-N. Conditions. Okay. Actually, some people say that Karush-Kuntaka condition with subconditions. But anyway, this Karush-Kuntaka conditions is also very interesting. It's also a kind of result. So since this is a theorem, it also is in this form. If something is true, then you have a consequence. Interestingly, this Karush-Kuntaka condition has almost the same if part as the complementary slackness. So as you remember, if x star is primal optimal and lambda star, nu star is dual optimal, and P star equals D star, strong duality holds. So far the same as the complementary slackness, but you have one more condition, that is, and F0 and F underscore are differentiable. Of course, on D, the domain of the functions. Got it? Then we have some result. Actually, this Karush-Kuntaka condition is this part. Okay. So it's like this. If you are a king, you are a human being, right? Then what is a necessary condition to be a king, human being, right? So this part is called Karush-Kuntaka conditions. So we are going to state the consequences of this strong duality and primal dual optimality and differentiability. And definitely, as you know, that there must be complementary slackness, right? Because of these three conditions. But first, let's state the constraints first. Since x star is primal optimal, it's primal feasible. So what do you have? You have f underscore x star is less than or equal to 0 vector, and h underscore of x star equals 0 vector. That is due to the fact that x is primarily feasible. Now second, lambda and nu are dual feasible. What do we have? Lambda star is greater than or equal to 0. So this is the first condition. That is second consequence. What is third one? Third one is the complementary slackness we've just seen. So lambda star transpose f underscore x star equals 0. Okay? Be careful. This is a scalar, right? Because this is the inner product of two same length vectors. And the fourth one, is related to this differentiability. Why differentiability is so important? It's because of this. Remember, you want to minimize the Lagrangian dual function. So you wanted to infimize f0 of x plus f underscore of x, lambda transpose f underscore of x plus lambda transpose f underscore and nu transpose h underscore subject to x in D, right? Suppose we have chosen omega prime as D, the domain of these two functions, these three functions. Okay. Now, we assumed, h is also differentiable. Okay. So they are differentiable on D. Now, how can you find an optimal solution of this one when you have differentiability? First order necessary condition you use, right? So we differentiate this L with respect to X. Then what do we have? Now so we view L as a function only of X, right? Because we infimize of X. So we differentiate and set it to 0. So first we have gradient of f0 of X plus. Now, how can we differentiate this term with respect to X? Confusing? Then we write this one as summation of lambda I and fi of X. Then each term can be now differentiated. What? Lambda I gradient of f sub I. So here we have lambda I times gradient of fi of X. Now, similarly, the third term becomes nu I hi of X. Okay. So this is the gradient of L with respect to X. Now, what does this mean? This is primal optimal, dual optimal, P equals D, which means that if you evaluate this Lagrangian, the gradient at x star and lambda star nu star, it must be equal to 0 vector. So now let me use J, because their lengths may be different. Gradient. Okay, so this is simple first order necessary condition. Got it? So this is another consequence of assuming this and differentiability. Got it? Without differentiability, you can't say this. Am I right? Because some of the gradients may not exist. Right? Now, what's the use of this one? What's the use of this kind of simple theorem or lemma? Suppose you want to find the triplet x star, lambda star, nu star. When you are given a primal problem and you successfully formulated a dual problem. You want to find the x star, lambda star, nu star triplet, but suppose you don't know how. This gives you an idea. You find a triplet, any triplet. For example, every triplet x lambda nu satisfying these four conditions. Then what can you say? If this holds, one of the triplets must be the optimal triplets, right? Right? So you have a necessary condition. You have a necessary condition for primal dual optimal solutions to satisfy. When what? Strong duality holds and functions are differentiable. Got it? And you may say that it may not be that useful, but no. Okay, I've written one of research papers with my former graduate student to solve very complicated optimization problem by using them. Actually, the problem was complicated, so we had a few conditions, different cases, and each case has its own optimization problem. What we did was that we just find out every triplet for each problem. Here, important is every. Okay, sometimes it's not that difficult. Okay, you just do not find just one triplet that satisfies this one. You find every triplet satisfies this condition, and you just evaluate the objective function, and you find the triplet that minimizes the objective function. That is optimal. Got it? So this kind of necessary condition is often very, very useful. So that's why this complementary slackness, this one, and this Cauchy-Kuhn-Tucker conditions, four conditions, is important. I would say collectively these four conditions as a single necessary condition for primal dual optimality. But anyway, Stephen Boyce and his co-author just wants these each conditions to be satisfied. Anyway, sometimes you see Kuhn-Tucker conditions. It's not different from this one. They are the same. The reason is that after they published this result, some people found that long ago this guy Karush have already stated this result. That's why some people say KKT conditions, Cauchy-Kuhn-Tucker conditions, or sometimes just Kuhn-Tucker conditions. They are the same. Got it? Now, we have a very special case. The special case is this. I'd better say that convex problems and KKT conditions. Here, convex problems are in the standard form. Standard form. What does that mean? the equality constraint function is an affine function, ax minus b. So given minimization of x0 over x subject to f underscore is less than or equal to 0 and ax equals b. And of course, they are convex functions on the domain. Here goes another statement. X tilde, lambda tilde, nu tilde. A triplet, a primal and dual variables triplet. Is optimal. If and only if it satisfies the KKT conditions. Okay. Very nice result. Okay. In the previous page, we just assumed general constrained optimization problems with inequality constraint function and equality constraint function, right? But now we restricted our interest to a very small set. This one, right? This small set. Before, the complementary slackness was about this set, right? And KKT condition was applicable to this set. Now we restrict our attention to the smaller set, and we have this if and only if condition. So what does this say? Suppose you are given a convex optimization problem in a standard form. Then, in order to find the primal optimal solution, what you do is that you formulate the dual problem. And then you try to find every triplet of x lambda nu such that they satisfy dual feasibility condition, primal feasibility condition, second, dual feasibility condition, third, complementary slackness, fourth, what? Oh, by the way, we should assume that they are differentiable. Suppose we have found such triplets, then what does this say? Each triplet is optimal. Okay? They must achieve the same P star and D star, which must be the same, right? And they are optimal. So this is more stronger condition, but because we have convexity, but it's also very, very useful because there are many convex optimization problems in the standard form. Now let's prove this result. Let's take a look at the Lagrangian. The Lagrangian is a little bit different due to our assumption that this problem is in the standard form. Let's write it down. So we have the first term, the objective function. We have the second term, lambda transpose f underscore x. So far the same, but here goes the very different part. Nu transpose ax minus b. Got it? What is this function as a function of x? A convex function. what is this function as a function of x? It's a convex function. Because lambda is greater than or equal to 0. Summation of convex functions is a convex function. Now what about this? Each entry is what? Is an affine function. Interesting property of an affine function is this. If you multiply some constant, whether it is 0, let's forget about 0, plus, negative, plus or minus, the function is still convex. The straight line is convex at the same time concave. So what is this? This is a convex function of x. Okay. So this is a convex function of x. Now we have what? We have differentiability, right? So the first condition, first KKT condition says that g of lambda tilde nu tilde equals L of x tilde lambda tilde nu tilde. Why is this so? Why is this so? Because our first condition, what was that? Of the KKT condition. The first order necessary condition. If L is convex and differentiable, this is differentiable, right? That is not only necessary but also sufficient. Okay? So this holds. And this is nothing but f of x tilde, f0 of x tilde, and this is d star, also at the same time p star. Okay, so this is due to the strong duality assumption, right? Strong duality assumption. This is differentiability and convexity. So what? X tilde is what? X star, one of x stars. And definitely lambda tilde and u tilde is one of the dual optimal pair. Got it? So this is the proof. You may not quite sure about the proof because you are not much exposed to convex functions and convex sets and convex optimization problems. But just remember this. Okay? First, the definition of the complementary slackness comes from what? General constraint optimization problems with equality and inequality constraint functions. Second, the KKT conditions comes from what? Primal optimality, dual optimality, and the differentiability. Third, the necessary sufficiency of the KKT conditions comes with what? The assumption of standard form convex optimization problem. Got it? So we restrict our attention little bit. Now let's see one important example. If you take a look at the lecture note, they have one example named water filling. And some of you who have taken the information theory or who are taking information theory course may know this one or may have heard of this one or you will hear of that one. The problem looks like this. You want to maximize over x of summation of log 1 plus sigma I square xi, yeah, subject to xi's are all greater than or equal to 0, and summation of xi is less than or equal to some p. Okay, so the original problem from the information theory looks like this. But you may say that, oh, wait a minute, the problem is different from the textbook. Textbook has this problem, minimize minus summation I log xi plus alpha I subject to x greater than or equal to 0 and 1 transpose x equals 1. Are they different or are they the same? Let's compare one by one. First, objective function. Are they the same? Here we have maximization, here we have minimization, but with minus sign. So we can drop this minus sign and change this to maximization. So maximization and maximization. Now we have summation of log xi plus alpha I, and it seems that they look different, but actually not, because let's rewrite this one as log sigma I square plus xi. Then what do we have? Log sigma I squared plus xi minus log sigma I squared. So if you sum out, this term will be summed up over I. But as you already know, in maximization problem or minimization problem, constant term doesn't affect our optimal solution. It only affects the optimal value, right? And now let's compare these two. And x is the variable. So you can say that alpha I is sigma I squared. So actually, the problem, the maximization and the objective function are equivalent, right? I'm not saying that they are the same problem. I'm saying that they are equivalent. Now, let's see the constraint. If you rewrite this condition in a vector form, x is greater than or equal to the 0 vector. So far, so good. Am I right? Now, you may say that, wait a minute, this has upper bound in the summation of xi, but this has equality and 1. But actually, if you change this to p, by the way, p positive, okay? And if you properly scale, actually they are the same. Okay? So this 1 doesn't matter, but it seems that it has 2 inequality constraints, but this has 1 equality and 1 inequality constraint. Am I right? But they are still equivalent. First, suppose this condition is the optimal solution satisfy this constraint with inequality, strict inequality. What does that mean? You can increase some xi, right? So that you can meet the equality. Am I right? But what happens? If you increase xi, log 1 plus xi over sigma I square always increases. With other xi's are fixed. What does that mean? The optimal solution must satisfy the equality. Got it? So you can change this constraint to equality constraint in this case. Okay? Got it? So now this problem is equivalent to this problem. Got it? So sometimes you should be careful in dealing with inequality constraints. But be careful. The reason why we can change this to equality is because of our objective function. Just taking a look at the constraint set, you may not be able to remove this. You must take a look at the objective function and need some reasoning, some proof by contradiction. Got it? Be careful. By the way, what about this? You have some resource P, total resource P, and you distribute this P to some xi's. Am I right? And this resource, total resource, is positive, and distributed resource must be non-negative. Such problem is called resource allocation problem. And this is one famous problem in information theory. There are many resource allocation problems. And most of them has some constraint like this. Got it? Now let's draw this one in three-dimensional space. x1, x2, x3. Now, what does this mean? Your x vector is in the first orthant, right? And second, summation is less than or equal to p, which means that you have the simplex and you also include this inside contained by these four triangles. It is different from the probability simplex, right? It's not a simplex actually. You have one simplex and another one, another one, another one. Okay. In three-dimensional case, you have four simplex and it's inside. Got it? So every resource allocation problem have the constraint set looks like this. In three dimension, in similar thing in higher dimensional space. Got it? I'm not saying that, let me repeat, I'm not saying that you can always just consider this simplex. It depends on your objective function. Fortunately, in this problem, in this special resource allocation problem, our optimal solution must reside on this simplex, the triangle in this case. Got it? Because we have equality. This is very important. You will see in the exam. Anyway, I really love resource allocation problems. Now, let's try to solve this one by using our KKT conditions. Okay. Now, first, is this objective function a convex function? Actually, no. Okay? But in this form, okay, this negative logarithm is what? It looks like this, right? It's a convex function, and you have summation of convex functions, so it's convex. And you know that this set is convex because it's a what? It's a probability simplex, right? Because we have one. It's convex. So this is a convex optimization problem. So whenever you hear that the problem, you find that our primary problem is convex, what? There must be a ringing Pavlov's bell, and you must do the like, okay, I need to apply KKT conditions. Okay, you must have that kind of reflex. Now, let's find that. So the first thing you need to do is to formulate the Lagrangian function. What is that? Summation of log 1 plus xi over sigma I squared. Here, minus lambda transpose x. Okay? And here I use negative sign. And lambda transpose x. Why? Because I want to find the lower bound, right? This is non-negative and this is non-negative. So I put negative sign here. Got it? Don't be confused. Usually we have plus and lambda transpose and minus x, but it's the same, right? And now we have another one, equality constraint function, 1 minus or 1 transpose x. Got it? So the Lagrange multiplier associated with the inequality constraint functions is a vector, and that associated with the inequality is a scalar. We have single scalar equality constraint. Let me use P. Okay. Is it? Am I correct? Let me see. We have convex problem. Yeah. Sorry, concave problem. It's really confusing. Okay. See that? This is. I'd better use like this. Here, minus, right? Yeah. Then objective, and we subtract, right? Got it? Now, what do we do? We differentiate the Lagrangian and find the triplet that satisfies this equals 0. So we have what? I hope I'm correct. Okay. 1 plus. By the way, let's assume that this is natural log. Okay. Let's see the ith entry. What does that mean? We differentiate this L with respect to xi. Okay, then this is the first term. And the second term is, okay, is it? Am I correct? We should have plus, right? Yeah, it's really let me see. Lambda I is positive. Okay, lambda I is positive, xi is positive. Sorry, okay. So negative is correct. So this becomes lambda I, right? Because we have summation of lambda I and xi's, and if we differentiate with respect to xi, we have lambda I. And here we have nu. Am I right? Now, we want to find the pair of x lambda nu, x tilde, lambda tilde, nu tilde, satisfying this equals 0 for all I. Okay, so we want to find is this all? No, we also must satisfy the feasibility, the primal feasibility, dual feasibility, and the complementary slackness. What is the complementary slackness? If xi is positive, what? Lambda I must be 0. Am I right? This is complementary slackness. So, there are two cases. Case 1, xi tilde is positive. So we have, now let's multiply sigma I squared, so we have the same thing. Sigma I squared plus xi minus nu tilde equals 0. Case 2, xi tilde is 0. Then we have sigma I squared plus xi tilde plus lambda I tilde minus nu. Sorry, minus. Am I right? See that we differentiated the Lagrangian function and want to set this equals 0. We have many constraint, scalar equality constraints, and some of xi's, x tilde i's, is positive, some not, right? But when we have this, lambda must be 0 by complementary slackness. So we have this condition. Now we can solve for this one. And it says what? Sigma I squared plus xi tilde equals minus 1 over nu tilde. Am I right? You move this and flip, then you have this. So here xi tilde equals minus 1 over nu tilde minus sigma I squared. And this must be what? Greater than 0. For this one, x is 0, so we have to delete this one. Now, we use the primal feasibility. What is that? Primal feasibility says that if we add up xi's, then it must be 1. But such xi is 0, so we just add up these things. Summation. And now you see here sigma I squares are given, right? Right? And this is function only of nu. Am I right? So we want to find nu tilde that satisfies this equality. Here, this is P. Okay. But each term must be greater than 0. Okay. Actually, it could be 0 because in this case. So actually, what we need to solve is this one. We want to find nu tilde that satisfies this one. Okay. And what is this one? If you change this to nu prime, okay, the interpretation of this one is like this. Suppose you have I, 1, 2, 3, 4. Ignore the width. Let's say that this height is alpha 1, sigma 1 squared, sigma 2 squared, sigma 3 squared, sigma 4 squared. Now, you choose some nu prime, okay? Nu prime, so that the difference between nu prime and sigma 1 squared, nu prime and sigma 2 squared, nu prime and sigma 3 squared, and not this one here, because in that case it's negative, okay? Equals what? Equals P. So what you do is that you change nu from 0 to infinity, and so you perform a one-dimensional line search so that this equals. And actually there is a single unique solution. For example, if depending on this p-value and sigma I value, you may have something like this. This is nu prime. And then, let's assume the width is 1. Then this looks like water filling given a basin with height sigma 1 square, sigma 2 square, sigma 3 square, sigma 4 square. That's why we call this problem as this solution is a water filling solution. Got it? So we are done. Okay? We just find this way. Okay? And you can show that if you find that way, then you find some lambda I so that is equals 0. It doesn't matter. Lambda i's for this case does not affect our problem. Right? Anyway, so after you find lambda tilde, that is minus 1 over nu prime, what? You just find lambda I. Because if you move to right hand side, then this minus that one from here must be positive. You can show that if this is true, if you remove that one, this part is always positive. Okay? So it satisfies our dual feasibility. Got it? You need to check actually. Dual feasibility is also true. Okay? So we've seen the water filling solution. Okay, time's quite up. This Wednesday, we are going to finish the perturbation and sensitivity analysis. And then we will go back to our original textbook about duality of the linear programming. Then we kind of wrap up with this one. Then we move to the next chapter of our textbook that actually explains what's the meaning of this Lagrangian Lagrange multipliers and sometimes called KKT multipliers. Okay, and we will study multi-criterion optimization problem and some variational problems, and then finish this course. Okay, that's all for the day.